Good morning, my name is Samantha Riles from Sugar Research Australia, and I'd like to welcome you to our first milling webinar for 2020. Today, Anthony Mann from Queensland University of Technology will be presenting on the topic, boiler simulation as a tool for operator training. Please note that today's webinar is being recorded and a copy of it and the slides will be sent to all registrants. Throughout the presentation, all attendees will be on mute. If you are having any technology issues, please send a message in the chat box, which is located on the menu bar of your webinar screen. If you experience any issues in hearing the sound coming from your computer, please feel free to join via phone, and I have put this number in the chat box. I will be assisting as a co-host to ensure that all runs smoothly. We encourage you to take an active part in today's webinar by asking questions. As this webinar is in listen-only mode, you can do this at any time throughout the webinar by typing your question into the Q&A button on the menu bar. At the end of the presentation, there will be an opportunity for Anthony to answer those questions. I'd now like to hand over to our presenter for today, Anthony. Thank you.
Yeah, thanks, Sam, for the introduction. Yeah, this webinar is on using boiler simulation as a tool for operator training. So basically, the driver behind this work is the industry's desire to invest in its people, because we know there are increasing cost pressures. The control systems that we use to run the factories are getting more complicated, and workplace health and safety requirements are becoming more and more stringent. We expect more of our staff and our operators, and many operators need to be multi-skilled and not just work on one station and one part of the factory. And we also like to minimise staff turnover, because every time you have a staff member leaves, someone new has to come in, get up to speed in that role, and to get to the level of the person that they were replacing. So it's very important that we do this, because really, when you think of it, our people are our only really sustainable long-term competitive advantage. The boiler station is probably the most important part of the sugar factory, because most factory operations require steam, and steam is produced by the boiler station. However, when you have factory disruptions, they disrupt the boiler station. And conversely, when you have boiler station disruptions, they affect the factory and therefore production. So the boiler operators are one of the most one of the most important group of people in the sugar factory, and the competence of boiler operators is absolutely essential. Boiler operators require a steam ticket before they're allowed to operate at the boilers. But as any operator would tell you, the steam ticket is only a first step on the path to becoming a competent operator. And traditionally, the industry has relied on on-the-job training or mentoring or a buddy system. So basically, operators learn from their colleagues. And there's also part of the learning process is operators being thrown in the deep end, like learning by experience, doing it themselves when they're the only one on site, or they're the only one at that particular time, and they have to make a decision at that particular time with no one else around. So the drivers for this project, which is developing a boiler simulator, were some recent well-publicised incidents. And some of these incidents cost in excess of $10 million for repairs and lost production. Whenever you make a major claim, insurance costs will undoubtedly increase, and you get greater external scrutiny, especially from regulators. These incidents in the boiler stations are an industry-wide issue, and therefore it requires an industry-wide response. So what are some of the things that can go wrong in the boiler station? Some of the critical things that have contributed to some of the previous incidents are boiler drum level issues. Like if the boiler drum level gets too low, you can overheat your boiler and severely damage it. If your drum level gets too high, you can cause carryover of water droplets into the superheater tubes, causing failures of the superheater tubes, or water droplets carried over into the factory turbines and cause failures of the turbines. You can also get steam pressure fluctuations, and steam pressure fluctuations can cause turbine trips and therefore factory stoppages. In the boiler station, you also have issues with instrumentation and equipment failure, and other issues associated with puffs or explosions. So basically resulting from unstable combustion that occurs during normal operation or startup problems. So this photo here just shows the consequence of a boiler explosion. See here, we've got an electrostatic precipitator being knocked over. And this is due to a boiler explosion, and this boiler explosion was partly attributed to operator error. So the industry response to these issues is multifaceted. Firstly, the industry has been developing standard operating procedures for the boiler station. The industry is developing more formalised operating training processes. And also the industry is looking at training simulators. And that is basically this current project. And a really encouraging aspect of this project is that we've been able to get input from all milling companies. So some of the training simulator options that have been looked at, the first and fanciest is the site-specific or replicator simulator. So basically in this site-specific replicator simulator, the processes are simulated and the human-machine interface is identical to the distributed control system that the operators would normally see. This site-specific replica type simulator is ideal for replicating the plant response and also for training operators with the human-machine interface. However, the site-specific replicator simulator is very high cost, well over $1 million. And another disadvantage of the site-specific replicator simulator is that when you do change the DCS, which often happens when a new bit of equipment is installed, then the simulator has to be upgraded. So that entails extra costs. Another type of simulator is the type-specific. It's operated by a company called Costex Systems. So this type-specific simulator has a similar back-end to a replicator simulator, but the human-machine interface is similar to the DCS interface or distributed control system interface, but not identical. And these specific type simulator, they're around about a quarter of the cost of the site-specific replicator simulator. So the site-specific replicator simulator, an example of that is at Tarong Power Station, and Millmerran Power Station has a type-specific simulator. The third simulator training option is the generic simulator. The generic simulator has a back end that approximates the different processes in the plant and also predicts the plant response to changes. So this generic simulator has some value for training in how the plant and the boiler station responds to changes. A generic simulator has an interface that is designed not to match any DCS interface, so has very little or no value for training operators in the HMI or human-machine interface. But the main advantage of a train generic simulator, it is much, much lower cost. So this project, which is just recently completed last year, SRA funded by SRA, started in the middle of 2016, the budget around $200,000. And basically, the idea of the project is to develop a simulator that can be used for operator training and refresher training of operators, and not just for operators, but also supervisors as well. So the simulator development process consisted of quite a few stages. At the start of the project, we had surveys of boiler operators and also industry survey, which is generally chief engineers, production managers and factory managers. And then we had an industry workshop hosted by Kai Sugar at Plaistow Sugar Mill. And then the fourth stage of the process was when we developed all these simulator submodels. Following that, we combined those submodels into our back end for the simulator. And then after that, developed a front end for the generic simulator. After developing that front end, I had an initial demonstration of the simulator, and that was at the Wilmar Townsville office, and that was a very useful session because Wilmar have a fair bit of experience with simulators for boilers and pans and other parts of the factory. So they provided some very good feedback, which was incorporated into the simulator. And then at the final stage of the project early last year, we had a demonstration of the simulator at Milliquin Mill. So this generic simulator developed in the process, in the project, as the back end, which is based on submodels that are physically based. These submodels were written and tested in Visual Basic, and then transferred these Visual Basic models into SysCAD, which is a process simulation package, and it has a macro or module language, PGM, and the SysCAD VB was incorporated, or the VB was incorporated into SysCAD, and SysCAD supplies steam and water properties, controller functionality, and equation solvers. Furthermore, the SysCAD also provides a generic front end for the simulator, and this generic front end can be customised based on the feedback. So the back-end components, or the submodels of the simulator back-end, include heat transfer correlations for the various parts of the boiler, including furnace, screen, superheater, convection bank, air heater, and economiser. And also models that simulate the gas, air, and water and steam systems. So it takes into account, includes fan and pump curves for the dampers and control valves, correlations for the pressure drop in the grate and dust collector, also relationships for stack effect, also flow inside the tubes, flow through the tube banks, and also models of the steam drum. So they're very important for the simulator back end to predict swell and shrink of the drum. So basically, that is the rise and the fall of the water level in the boiler steam drum. So swell is when the water level in the steam drum rises. That occurs when the steam flow leaving the drum is greater than the net steam flow in the boiler. So what happened in the boiler? So basically, the steam is produced in the furnace tubes, screen tubes, convection bank tubes, and there's also condensation in the drum. That condensation is what supplies the energy for heating the feed water up to the drum temperature. So when you have swell, the steam leaving the drum, the steam flow leaving the drum is more than the net rate of steam generation. That causes pressure in the drum to reduce, the density of the steam reduces, and that means that the steam, the bubbles below the water level expand, and that causes the water level in the drum to rise. Shrink is the opposite effect. So basically, when the steam flow leaving the drum is less than the net steam generation in the boiler. So basically, opposite happens. Basically, the pressure in the drum increases, the steam pressure increases, the steam density increases, and therefore the bubbles underneath the water reduce in size and the water level falls. So basically, swell is the issue that can cause failure of the superheater tubes and failure of the turbines. Shrink is what happens when your boiler level goes down and your boiler tubes can cook because there's no water in them to keep them cool. So the front end of the simulator uses the SysCAD plant simulation software for the generic interface. It can carry out steady state or dynamic modelling, and it also has trending capabilities similar to the distributed control system trends. You can write scripts in SysCAD, and they can be used in a training program. The interface isn't as detailed as the factory DCS interface, but it's significantly lower cost. So here just is a screenshot of the simulator front end. Basically, we have the furnace here, the screen tubes here at the exit of the furnace, the superheater, representation of the convection bank, an economizer, an air heater, dust collector, induced draft fan with some dampers going into the stack. And we have steam producing the superheated steam, just goes to the factory, supplies the factory steam, which goes to the shredders, the milling train, the turbo alternators and makeup valve, and then to the LP steam users and the LP vent. So this front end also has bars that here includes, like this particular representation has 4 feeders, and it just shows the feeder speeds as bars, and it also shows the drum level as a bar, dynamic bar as well. Here we've got little controllers for different components of the training program. So in the actual simulator, we can just double click on one of these and activate one of these controllers, and it'll go through a predefined command script that we can use for training. And here just some other part of the simulator front end. We've got the input screens, we've got input screens for the flow controller, and also input screens for the boiler controller. So as you can see here, we can adjust, there's a lot of parameters here that we can adjust to tailor the simulator to be more like the boiler station at a particular factory. And the simulator front end also has trending capability. And these trends can be shown in steady state or dynamic mode. And basically trends along here, time across the x-axis, and the different values here, the measured value here, and those measured values are also shown on the trends. So the training program that was developed as part of the simulator basically was to sort of help trainee operators with the response to various scenarios. So the training program developed in the project is we try to avoid the site-specific details and keep it very general. So some of the scenarios that are included in the training program are the load swing. So for example of that, like a pan comes online, or the shredder steam demand increases due to the variety of cane, or we have a reduction in steam load, like a pan coming offline, or a factory stop. Another scenario modelled in the training program is the having wet fuel, and also included scenarios, like the other included scenarios are loss of combustion and unstable combustion. So here we've just got a little demonstration video of the load increase scenario. So in this scenario, we've got a boiler, this test boiler, 200 tonne an hour maximum continuous rating steam load. The steam flow is starting off at 170 tonnes an hour and increasing in 3 tonne per hour increments. And so we'll get this going. Here we go. Okay. Okay, so we're running the command script for the load increase, and we've got variables in the top figure. We've got the boiler master in white, the steam flow to the factory in green, the steam temperature in red, and we've got the various gas exit temperatures, convection bank gas exit temperature in yellow, air heater gas exit temperature in dark blue, and economiser gas exit temperature in light blue. In the bottom trends, we got the drum level in white, steam pressure in yellow, drum pressure in red, and steam flow to the factory in dark blue. So you can see sort of just after we have a load increase, steam flow to factory increases, the drum and steam pressure reduce, the drum level increases, and we have steam flow to, as in the top trend, as the steam flow to the factory increases, we have the boiler master increases to maintain the steam pressure, and all the gas exit temperatures increase. Then when we have the next increment, we have then eventually the control system sets the drum level back to its normal values and the steam pressures and the process continues. Okay, well, thank you very much. This is just a final demonstration of the simulator. We'll also be talking about this at the ASCT conference in Bundaberg in about over a month's time. But I'd like to acknowledge SRA for funding this work and the respondents to the boiler operator and industry surveys, and also the participants at all the workshops, the industry workshop hosted by Mackay Sugar, the initial demonstration hosted by Wilmar, and the final demonstration hosted by Bundaberg Sugar, and all the attendees at those workshops that supplied very useful input. And also like to acknowledge those companies, Mackay Sugar, Wilmar, Bundaberg Sugar. Also like to acknowledge Mary Wang at KWA, Kenwalt. They're the suppliers of the SysCAD package. And also, last but not least, the ASMC People and Safety Committee that provide the initial driver for this work. Thank you.
Okay, thanks Anthony for that. I can't see any questions at the moment in the Q&A, but feel free to populate those in there as I just do my sign off here, and I can go back to them. Now's your opportunity to ask any questions. Thank you all for attending our first SRA milling webinar. We hope that you found it of value and are keen to get feedback from you. Tomorrow you will receive an email with the recording of this webinar and the slides and a link to a survey that we'd like you to complete. It will only take a few minutes of your time and allows us to improve our webinars in the future. Our next milling webinar will be held on the 11th of March and will be presented by Dr. Iman Ashanti from QUT, who will speak about falling film plate evaporator at Bingara. Please go to the SRA webpage to see any of our other upcoming webinar topics, and don't forget you can also view recordings from last year. I've just got a question in the Q&A that I'll go back to now, just bear with me. Okay, question here for you, Anthony. Will the simulator have a data interface, UDP, etc., to allow it to be directly interfaced with an actual DCS?
Yes, the simulator already reads and writes data from these Excel or comma-separated variable files. So that's quite, from my side of the thing, that's not very difficult to do. But from the factory side of things, some people at the different factories have said it may be possible to get the data from these comma CSV files, extract data from their system, put it into the simulator, and have the simulator send data back to the factory DCS system. Yeah, so it's possible on this generic, the SysCAD side of things to do that. And it may be possible to do that on the factory side, but that would require some input from factory control people.
Okay, thanks, Anthony. We have another question here. Does the wet fuel simulation just consider the heat required to vaporize the extra water, or does it consider the impact on combustion?
It does both. It basically takes into account the reduced heating value due to the heat required to evaporate the moisture. So it'll basically predict what happens after that. So basically there's less steam generation, you have reduced steam pressure, and that will cause swell in the drum, and it will also cause a reduction in all your gas temperatures till the feeder speeds start to increase as well. So it's, at the moment, the training scenario with the wet fuel hasn't got to 55, 56% moisture, where your combustion basically ceases completely or gets terrible, but that can be put in as sort of, I can modify what, in the training script, I can adjust artificially the unburnt fuel level too, so that will take that into account too. So the training scenario as is sort of predicts the effect of sort of going, say, from 50 to 52, 53% moisture, but not like a catastrophic increase in moisture. But that can be done in the future, and that's not difficult for me to do.
Okay, thanks, Anthony. So we'll provide Anthony's contact details on the email that will come around tomorrow with the recording and the slides. And I'm sure he will not mind you getting in touch with him with any further questions or comments. And thanks for all attending today. That looks like all of our questions for this morning. So thank you to Anthony, and thank you to our attendees for coming along.
Yeah, thank you all.
Thanks.
Thank you. Thanks, Sam.